I'm Nicole Carlson. Today I'm here to talk about a custom PyMC3 class I built that mimics the scikit-learn API. There's a link to my Twitter at the bottom as well as the slides for this talk. A little bit about me. Currently I'm a data scientist at ShopRunner. I also teach for Girls Who Code on the weekends, and like many people here, I'm a reformed physicist. All right, here's a brief overview of the talk. First, I'll do a quick motivating example of basic linear regression in scikit-learn. I'll talk a little bit about the PyMC3 library. We'll do the same linear regression example in PyMC3. Then I will compare scikit-learn and PyMC3, and the bulk of the talk will be the last two bullet points, implementing a custom hierarchical logistic regression class in PyMC3, and then using that class. All right. So to start out with, we'll do a really simple example with scikit-learn. First, we're going to generate some fake data. So we'll have some random values for x, some noise of size 2, and then our y values will be 4x plus 3 plus the noise. So if we go ahead and plot that data, it looks linear, which is good because I made it. All right. So if you had that data and you decided you wanted to use scikit-learn to fit a linear regression, it's really straightforward. You instantiate a linear regression instance. You call fit on that on your data set, and you get back a fit model. Once you have your trained model, you can use it to predict data. You can score your model. Here we can see the score of this model is about 79%. And we can also plot the model in this red line. And it looks like it fits the data pretty well. Once you have your trained model, oftentimes you'll want to save and use your model at a later date. Also very straightforward with scikit-learn. You can just use pickle to dump your model to a pickle file. If you open it back up later, you can call score again, and you see that you get back the exact same score. This is really the same model that you saved before. All right, so I imagine most of you have used scikit-learn before, and you'll probably agree that it's very easy and straightforward to use. Finding model parameters is really easy, predicting, scoring a model, as well as saving and loading a trained model, all very easy. So now we can think about PyMC3. If you're not familiar with PyMC3, I'll give you a brief overview here. There's going to be a couple of other talks about PyMC3 that'll probably go more into depth of the theory. But basically, it's a library for probabilistic modeling. So with this type of modeling, you parameterize your model in some way. With the linear regression, our model is a plus bx. And we say that our a and b are drawn from some distributions that we want to discover. And there's a couple ways to determine the distributions. So one is using Markov chain Monte Carlo samplers. The way I like to think about those is that you're walking around in parameter space, choosing random values for the parameters, deciding whether to keep them or not based on some cost function. Another more recent method are variational fitting algorithms. So with those, you have your true distribution of your parameters and your current distribution, and you minimize some metric between those distributions. So one example would be the Kublick-Leibler divergence between those two, but there's new algorithms coming out basically every day. PyMC3 is built on top of Theano. As you may know, Theano's ending, so I think they're choosing some new backend now. Don't know what it's going to be. And it's completely written in Python, which is why I chose it initially. I wanted to be able to go into the source code if I ran into any problems. When you're using PyMC3, you're going to follow basically the same 3 or 4 basic steps every time. The first is setup. You need to parameterize your model. So with the linear regression, our parameterization is that y is normally distributed around some linear combination of the variables alpha plus beta x. We choose priors for alpha and beta, and we insert our training data. The second step is inference. You're going to infer your parameters using either MC-MC sampling or variational inference, or both. The third step is interpretation. You need to check your parameter distributions and model fit and make sure everything makes sense. This step doesn't exist in scikit-learn. This is kind of a new thing with PyMC3. And a lot of times you'll just stop there because what you care about is the parameter distributions. But if you want to, you can also predict data by creating posterior samples with your inferred parameters. All right, so now we're going to do the exact same linear regression example, but in PyMC3. So first step, set up the PyMC3 model. So the first thing you do is instantiate a PyMC3 model instance. Then we're going to set our model input and output as Theano shared variables. This allows us to change their values later. And then we actually parameterize the model. So I'm actually going to start at the bottom with y. So as I was saying, our parameterization is that our y data is normally distributed with a mean that is a linear combination of our input variables, alpha plus beta x, and we also know that there's some noise s. Alpha, beta, and s are the parameters that we need to find the distributions for. In this case, we don't know anything about alpha and beta. We just know their numbers. So one good prior distribution for that is to say they're normally distributed with mean 0 and standard deviation 100. This is the point where Bayesian modeling is really powerful. If you knew something about alpha and beta, you could put that information into the prior distributions. So if you knew alpha was positive for some reason, you could put that right into your model. Our noise S, all we know is that it's positive, so we'll say that it's half normal. All right, now that our model is set up, we have to infer our parameters. So I actually use adv in this case, but you could also use a sampler if you wanted to. I instantiate an instance of the adv class, and then you just call the PyMC3 fit method, telling it how many iterations you want it to do and what method of inference you want. More replacements let you put different data in as you're fitting your model. In this case, I'm actually taking mini batches of the data. Mini batch adv is way faster than regular adv. If you have the opportunity to do it, I highly recommend using it. A model that I trained went from like 8 hours to like 20 minutes. Mini batches also help you avoid local maxima. So once your model has been fit with adv, you're going to look at something called the evidence lower bound, or elbow, which is helpfully stored in this property called hist for some reason in PyMC3, not sure why. And you can graph that to see if your model has converged. So what you want to see is that the elbow starts out at some lower value and then converges to some higher value, which we see here. Okay, so now we need to interpret our parameters. So our adv fit is giving us an approximation of the parameter distributions. I don't know about you, but if you just tell me a parameter is distributed with some mean and standard deviation, I'm not necessarily going to know what that means. So since we're Bayesian, when in doubt, sample. So we're going to sample from our parameter distributions, and we can just call sample on our approximation, tell it how many draws to take, and then that gives us a trace of our parameter values. With that trace, PyMC3 has some great functions to help you interpret those. One of them is summary. So summary gives you this nice printout of each variable, mean, standard deviations, other things you might want to know. Another nice function is called trace plot. This is the one I use the most often. So the trace plot, for each variable, you have a normalized histogram on the left, and on the right side is a time series of the parameter values. So since we are just sampling from a parameter distribution, it doesn't really change that much over time. If this was samples from an MC sampler, you would see that they would start at 0 and then go to the final value. In this case, which looks to be around 3. And if you recall the data from earlier, it was y equals 3 plus 4x plus some size 2. So you can see that our model really is picturing up the structure of the data. Okay, so like I said, in a lot of cases, you found the parameters, you might just stop. But if you want to predict new data, you can create posterior predictive samples by using the sample PPC method from PyMC3, tell it what trace to use, what model to use, and how many samples you want. So in this case, I want 2,000 samples. This means that for each y data point, I have 2,000 samples. So we can look at this here. The red is the true data point, and the blue smears are the 2,000 samples for each data point. So unlike with scikit-learn's linear regression, you're not just getting a point estimate, you are getting a bunch of estimates for each data point. That may not be useful for you, so one thing you can do is just take the mean of all these samples and use that as a point estimate. So the The means are shown here in green. But you still have all this other data. So if for some reason you wanted to know the uncertainty of your values, you could take the standard deviation and do something with that if you wanted to. Once we have point estimates, we can also just call score, the R2 score, on this data. And you can see this model is also at about 79% accuracy. So we're getting the same performance that scikit-learn's linear regression did, which is good. All right, so as I was learning PyMC3, I ran into a few issues along the way. Most PyMC3 examples only exist in Jupyter notebooks, which is really awesome when you're talking to other data scientists. But when you try to productionalize a model, I found that engineers do not like Jupyter notebooks, no matter how well you comment them. I tried giving one to some engineers, and they were just like, what is this? Most examples also focus on training a model with one data set and don't demonstrate how to predict new data. It may not be obvious to you from the simple example we've just seen how you would actually put in a training or testing data set. And they definitely don't show you how to save your model for later use. It's not like scikit-learn where you just pickle the model itself. So the spoiler alert is that what you want to save is the trace. You don't need to save the PyMC3 model instance. You can always recreate that later. So if we compare the two libraries, everything's still easy in scikit-learn. PyMC3, things are a little harder. I would say finding model parameters is a medium difficulty. Once you parameterize your problem, you can relatively easily find the parameters by running inference. Predicting new data and scoring a model are more difficult. You have to figure out how to swap your data in and out, and saving and loading a trained model basically seem impossible when you're first starting out until you find that one Stack Overflow answer that's like 5 answers down. All right, so if you're like my boss, you look at this and you're like, why would I ever use PyMC3? So I added in an extra row. Scikit-learn has a limited number of model types available. They're very strict about what makes it into their API. The algorithms have to be really well tested. It has to meet their code requirements. On the other hand, with PyMC3, the model types you can build are very broad. Basically, if you can parameterize it, you should be able to infer the parameters. So you can end up doing a lot more than when you can, which is scikit-learn itself. So here's what I want to reproduce in PyMC3. I want a class where I can just call fit, predict, score, save, and load without having to think about all the details, just like I do with scikit-learn. So in order to do that, this is the mapping between scikit-learn and PyMC3. The fit step in scikit-learn corresponds to setup in PyMC3 and the inference step. Predict and score are the same, the fourth step, predict data. Save and load is going to be something new with PyMC3. And PyMC3 also has this additional interpretation step that you don't really have with scikit-learn. All right, so now we're going to get into even more code. I'm going to show you a custom hierarchical logistic regression class I implemented in PyMC3. If you're not familiar with hierarchical models, this is the type of model you would use if your data comes in some type of categories. So for example, if you had a bunch of algebra scores for tests for high school students, one level of your hierarchy might be the individual students, and another level might be the teachers themselves. So maybe the teacher that a student has some effect on how well they do on their test. Probably true. All right. As I was creating my custom class, I noticed that a number of the properties and methods I wrote were not specific to this particular model. So I decided to create a Bayesian model base class for reusable components. The base class has 2 methods, inference and set shared values. Set shared values just calls the Theano set value function on Theano shared variables. The child class has to implement the following methods: create model, fit, predict, and score. Okay. So now we can dig into the code. So first step, initializing the HLR class. You can see that this child HLR class calls the parent Bayesian model class. The parent Bayesian model class, in turn, calls the scikit-learn base estimator class. This means that you should be able to use this class with your favorite scikit-learn transformers in a pipeline, grid search, all the things you know and love. And we can look at the properties that are in this initialization. So one is the adv hist, or the elbow values. Another is the adv trace. We will save a cache model, the number of predictors, and the Theano shared variables. So these are things that every Bayesian model needs to save. And the child HLR class, in addition, will have this property that's the number of categories. So if you have some different child class, they might have other properties they need to save. All right, so now we'll get into fit. It's a big wall of code, but don't worry, we're going to walk through it all. So if we look at this fit function, you see it starts out just like scikit-learn. You put in your x and y data, and additionally, we have the categories for our data. The last two keyword arguments are for inference, and I'll explain them in a second as we go through. So if we walk through this code, first thing we do, pull out the number of categories, the number of predictors, pretty straightforward. Then we check if there's a cache PyMC3 model, and if not, we'll create that model. And this method is one of the child class methods, and I'll show you that in a second. Once we have our cache model, we need to create mini batches for the inference. So that's what I'm doing here, and you can specify the batch size using the batch size argument. Once we have our mini batches, we just call the parent inference method, because again, it doesn't depend on anything about the child class, and you can also tell it how many iterations you want it to run. So now we'll look at the create model method. This corresponds to step 1, set up the model. And one thing to note is that it doesn't take in any of the data, x, y, or categories. And again, that's because what you really need to save is the trace. Once you have a trace, you can set up a new PyMC3 model and use it with that. So if we walk through this, it should look relatively similar to the linear regression example. First thing we do is set up some Theano shared variables, model input, output, and additionally we have the categories. Then we're just going to throw those into a dictionary. We instantiate our PyMC3 model. And again, I'm going to jump to the bottom and work my way up. So since this is logistic regression, our output is true, false. So these will be the results of a Bernoulli distribution with the parameter that's the inverse logistic of the linear combination of the variables, alpha plus beta x. The difference in this case is that each alpha and beta depends on what category the data is in. So you can see we have 1 alpha per category and 1 beta per category per predictor. Since this is a hierarchical model, we want to show that all the alphas are related together and the betas. So the way we do that is by defining these hyperparameters, mu alpha, mu beta, sigma beta, and these are the means and standard deviations of the alpha and beta values. Just like with linear regression, we don't have that much knowledge about the hyperparameters, so we'll say the means are normally distributed and the standard deviations are half normally distributed. And again, if we had some prior knowledge, we could put that in here. All right, so now we have our PyMC3 model, and I'll show you the inference step that fit called. So this is the parent class method, inference. Just takes in the mini batches and the number of iterations you want to run. Just like linear regression, we're going to instantiate an instance of the adv inference, call fit, number of iterations, the method we want to use in the mini batches. Don't worry about callbacks, that has to do with convergence. Once we have our fit, I'm going to again draw some samples of the parameters and also save the adv hist values. All right. I call this inference. This is in particular mini batch adv. You could imagine implementing other forms of inference if that was better suited for your problem. All right. Since this is logistic regression, our output is true, false, but we may wish to know the probability of the data being true or false. So just like scikit-learn, I implemented a predict probabilities method. So I also called it predict proba. Should look relatively similar to scikit-learn. Takes in the x, and again, additionally, we have the categories for this type of data. I'll talk about the last argument in a second. But if we go through, the first thing it does is check if there's an adv trace. If there's not, then I raise this custom error telling you to run fit on the model before predict. And to reiterate again, it's because the trace is what's really important and what you need to save with your model. Once we ensure that we have a trace, we get the number of samples, and then we check if there's a cache model. In this case, it doesn't matter if there's a cache model or not, because if there's not, we just create a new one. All right, because we'll be using that same model with our existing trace. We call the parent set shared vars method to set the Theano shared variables with our input data. And then we can just call sample PPC as we did before, telling it what trace to use, what model, and how many samples we want. So again, we have 2,000 samples per data point, so we could just take the mean if we want to, or you may wish to have both the mean and the standard deviations returned if you want a measure of some uncertainty in your predictions. All right, predict, pretty straightforward, just calls predict proba, gets the probabilities, and then checks if they're greater than some threshold, in this case 0.5. If you wanted to make it more general, you could change this method so that it takes in a custom threshold. All right, score takes in x, y, just like scikit-learn, and additionally we have these categories. Then it just uses the scikit-learn accuracy score function and calculates the accuracy score based on your predictions. All right, so now we're at saving and loading. So the child class in this case has some extra parameters it wants to save, the number of categories, the number of predictors. So it puts those in a dictionary and sends those and calls the parent class's save method. The parent class's save method takes in a folder where you want to save your stuff and then uses joblib to save the adv trace and any custom parameters to that folder. So pretty straightforward. Load basically does the exact opposite of that. The child class calls the parent load first and then gets back the parameters and puts those in the properties. And the parent load class just loads the adv trace from whatever folder you tell it to, as well as any custom parameters. And that was all the code. So that was how I built my custom class. Now I can show you how you can actually use this class. So even if you didn't follow all of the code, you would still be able to use this class just like you would scikit-learn. So just like before, we're going to generate some fake data. In this case, we have 2 predictors and 2 categories. I'm setting mu alpha and sigma alpha equal to 5 and mu beta, sigma beta equal to 10 because I didn't want to bother sampling for those. So these are, again, are the hyperparameters in our model. And then we're going to sample for alpha and beta from those distributions. So here are our 2 alphas and our 4 betas. So once we have those values, we can generate some fake x data and then use that to generate the y data by just taking the linear combination of the values and setting it through an inverse logistic and then through a binomial. So in this case, I generated each category separately and then just concatenated everything together. And our categories are just labeled 0 and 1 in this case. All right, so now we have some fake data. And we decided we want to fit an HLR to this. So I load the class from my custom library, PS Toolkit. I instantiate an instance. And now if I want to train a model, I can just call fit and put in my x, y categories. And in this case, I wanted to change the default arguments. And now I have a trained HLR model. So with that model, I can predict and score. So here I can use predict proba to generate some probabilities for each data point. I can also get back true-false predictions, and I can score our model. So you can see it's doing about 98% accuracy. All right. If I want to save and load the model later, again, I set it up so that's really straightforward. Just call save and tell it where you want to keep your stuff. These are pickles, so they're in a pickle jar. And if I want to use this later, I instantiate a new instance of my class, tell it where the stuff is saved, and we can go ahead and run score again. You see it's also at about 98% accuracy. It's not the exact same because we're sampling every time. So this isn't like scikit-learn where you're going to get the exact same result. Due to the sampling, you're likely to get slightly different answers. But if you sample enough, that all should wash out. All right. So if you were following along, you may have noticed I skipped a step in the PyMC3 process, which is interpreting your parameters. But I built some extra methods into the class to allow you to easily do that as well. So one is this plot elbow function. This is a parent class method that just plots the elbow for you so you can see if your fit has converged or not. Since we saved the trace as a property, you can just call those same PyMC3 functions, either summary, where you get this nice printout. So here I'm showing you the alphas and betas again, and we can compare them against the trace plot. So the alphas are at like 7 and 11. Looks like it's heading that way. 2, 13, 18, 22. Yeah, looks like it's heading in the right direction. So the model really is picking up some of the structure in the data. The mu alphas and the mu betas aren't doing as well, but maybe I can change some stuff to get them to work. So it's still really easy to interpret the parameters with this custom class as well. So hopefully you'll agree that everything with my custom class is easy. To find model parameters, you just have to call fit. To predict new data, just call predict, score, call score. There are save and load methods, so as long as you know where you want to keep your stuff, it's easy. And it's also really straightforward to interpret the parameterization. So the last thing I want to talk about are some next steps. You may have noticed that I hard-coded a lot of values in. It's because I'm lazy. But if I wanted to, I could add those as keyword arguments that you could pass into the various methods to make this even more generalizable. As I mentioned, I only implemented mini-batch adv. There are tons of other types of inference that you could implement and maybe let the end user decide which method is best for their problem. And again, since this is built on a scikit-learn based estimator, you should be able to use this in a scikit-learn pipeline. So I would want to test that in my imaginary free time. All right, so that's basically it. I wanted to thank my coworkers at ShopRunner who helped me and gave me a lot of advice on this. We're hiring in Chicago. You should come work with us because I'm awesome, obviously. I gave a version of this talk at PyData Chicago in June, so I want to thank the community there for giving me feedback, as well as my former coworkers at ShiftGig who also helped me practice. Here's a link to the slides again, as well as the code for the custom HLR class. Thank you.
For making predictions, would you consider saving like the map estimates of the coefficients instead of sampling?
I've done that in other classes, but not this one. So yes, if I just wanted a point estimate, I would do that too.
Now, what's the burden on saving the whole trace versus, and I know you would lose some reproducibility or whatever else, but to be able to just save from that trace, what's the let's say mu and sigma of each point or whatever. That way you reduce the amount you have to save down to just a couple numbers per whatever. I know you lose whatever, but do you think that would be a useful save class by chance, just for save size-wise?
Yes. So he asked if you could just save the adv approximation instead of the trace. Yeah, you could definitely do that. You would save space, but you would also lose on time because it takes a while to do those samples.
Got it.
Yeah. The question was about using PyMC backends. Like what? SQLite and stuff like that. I ran into trouble with SQLite because I had too many variables, and they have a limit on the number of columns, so I gave up. I gave up on those. Yeah. I just pickled the traces, so. I'm not sure what you mean. I'm not sure. It was about compiling Theano. Theano cache is that, from the front row. Thank you.